All right, hey guys, I want to do a quick little video with you on predicting products for chemical reactions. So we're going to do these 6 problems, which is a mixed bag. There's some synthesis, there's some decompositions, some single replacements, and some double replacements. So let's kind of cover it all, brief overview of each of those things real quick as we try to wrap up this unit on chemical reactions and the last part of it, predicting the products. So we'll start with the first problem here. First problem, this is a really simple one because you just have 2 elements, right? So anytime you have 2 elements, all you can do reaction-wise is just to put those elements together. So we know this is going to be a synthesis reaction. It's just a metal and a non-metal. It's going to make a salt, right? So all we do is we simply just say, okay, we got Mg bonded to Cl. The metal always goes up front. The non-metal always goes in the back, right? And then you just do your swap and drop. We know that magnesium is a +2 because it's in group 2. We know that chlorine is a -1 because it's in group 17. So when you swap and drop, you get MgCl2, right? And there's nothing to do there. Of course, this was just notes for us, so we can erase the +2 and the -1 up top. That was just little notes for us. So if you got two elements, all you can do is put them together. On the decomposition side, if we had the opposite of that, if we started with this, we have 2 elements, all we can do is just bust them apart, right? So you would decompose something like this by just busting it apart to the 2 elements. And of course, if one of them is a diatomic like chlorine is, then you would put a 2 on it. You have your list of the diatomics, right? It's fluorine, chlorine, bromine, iodine, hydrogen, nitrogen, and oxygen are the 7 diatomics. Okay, so next of the synthesis, we have K2O, which is a potassium oxide, and then we have water, right? So how do I know this is a synthesis reaction and this isn't a double replacement? Because it is 2 compounds, right? Well, I know it's not a double replacement because I have oxygen in the back of both of them. If I have oxygen in the back of both of them, then I couldn't do a double replacement. Nothing would happen. You would still end up with the same 2 things, right? Another big hint is that you've got water, because on a lot of these guys, on several of these guys anyways, you end up with water, okay? So this is one of your reactants is water. This one's one of your reactants is water. This one you have oxygen. On this guy, you have both oxygens, right? It's a non-metal oxide and a metal oxide. So once again, it's this kind of scenario. And then this one, same thing. You got oxide and then a dioxide. So both oxygens in the back. This one you're going to have the same element again. So that's going to hint to you that it's not a single replacement or a double replacement. And of course, this one's just once again 2 things that you're putting together. Okay. The only one that might be a little tricky for you that you're thinking is like a single replacement, but it's actually a synthesis, is the metal chloride and the oxygen. Because you get a metal chloride, say you got your metal chloride and then you got your oxygen, you may think that's single replacement. But when we get to single replacements, you'll know that oxygen never replaces the chlorine there. When you look at your list of nonmetals, that for the single replacements, it's just the halogens, right? So that says, okay, that's not going to happen. It's not a single replacement, so that means it must be a synthesis, right? The synthesis can kind of look like the other ones. Okay, so we know this is a synthesis reaction, and we know that we have water, so it's one of these 2. It's a metal oxide. K is a metal, so we're going to do this one, and we're just going to make a metal hydroxide. So our metal is K. And then hydroxide, we know, is OH because we know our polyatomics, right? This guy's a +1, this guy's a -1. We just need one of each. So we already have it right. Now, you could put the OH in parentheses if you really want to, but we don't have to, okay? If I go on to the decomposition, remember my decompositions look almost the same, except they're just split, okay? So we have salt that's being broken apart into a metal or non-metal, or we have a metal oxide that's being broken apart into a metal and oxygen. Same thing, if I have 2 things, all I can do is just bust them apart. And then we have an acids break down to non-metal oxide and water. Metal hydroxides, like we just did, if we had something like this, then it would break apart into the metal oxide and water, right? Chlorates break down to metal chloride and oxygen. Salt with polyatomics, this is a generic one, right? we'd make some non-metal oxide and then some metal oxide. The metal oxide coming from whatever the metal of the salt is, and the non-metal oxide coming from whatever the non-metal that was in the polyatomic. And you got your metal carbonate, which breaks apart into a metal oxide and carbon dioxide. Once again, this is just a specific example of number 5. And then, like we said here, we're just busting that apart. We really didn't do a whole lot with hydrated salts. Told y'all you don't have to worry about that. So this guy, this is a metal, this is a polyatomic, right? So it's going to be, you know, one of the ones with polyatomics. It's not chlorate, it's not carbonate, it's not an acid because we don't have hydrogen up front here. We have a metal, it's not a hydroxide. So we're left with number 5, just to kind of rule it out, right? So we know we're going to make a non-metal oxide and a metal oxide. Like I said, the non-metal oxide is going to be made with the stuff that's in the polyatomic, right? N and O. And then the metal oxide, obviously your metal is calcium, and then you have your oxygen. So we have the parts. Now let's write the formulas right. I know calcium's a +2, oxygen's a -2, right? This one's in group 2, this is group 16. So you just need one of each of them since their charges are already balanced or neutralized. And then this guy, when we make these non-metal oxides, that's when we have to use our oxidations to go back and say, okay, what is the oxidation of the nitrogen in this case, right? So we know oxygens are negative. Let me write this in a different color. We know oxygens are -2s. There's 3 times 2, there's 6 of them. So 6 times -2, that gives me -12. I know the calcium is a +2, right? So I got 2 and then what to balance out this -12. Now obviously this would have to be a +10, right? And since this 2's out here, that means I actually have 2 nitrogens. So the nitrogen altogether is a +10, but you divide by 2, and it means each of the nitrogens are actually a +5. Okay? So with each of the nitrogens being +5 on that side, they're going to hold that same oxidation on the other side. So this nitrogen is going to be a +5. We know the oxygen is a -2. It's going to get the oxidation that it wants in most cases, right? So now we just have to figure out how to balance this out. We're not going to get a 5 with sets of 2s. You know, you got 2, 4, 6, 8, 10, that kind of thing, right? So that's never going to balance out. So if I will put a 2 on here and say, okay, now I got 2 nitrogens, that's a +10. So to get a -10 from here, I need 5 oxygens, right? So +5 times 2 gives me a +10. -2 times 5 gives me that -10. So the oxidations add to 0 like they're supposed to do on neutral compounds. Okay? Boom. That's it. And of course, the green stuff is just notes. It's not the answer. The answer is the black, right? So the next one. I know I only have one thing over here. There's no plus sign anywhere. And since there's no plus sign, that means that it is, once again, a decomposition, right? So which decomposition is it? If I recognize here, ClO3, I should immediately recognize as chlorate. So chlorate's one of my options. A metal chlorate makes metal chloride and oxygen. Well, that's easy enough. The metal is Fe. Obviously, chloride is Cl. And then oxygen is just O. Now, oxygen is a diatomic. It was one of those 7, so I have to write it with a 2. And then I got to go back and I got to write this formula right. Okay? So I know chlorine is -1, right? And then Fe is a transition metal, so it can have multiple oxidations. So I got to go back over here and look and see what its oxidation is. Now, in this case, since I'm looking for I'm not looking for the oxidation of this non-metal, but I'm just looking for the oxidation of the metal, then I can take this chlorate all together and say, okay, chlorate, the chlorate polyatomic is a -1. There's 3 of them, so that's a -3. So that means this guy would have to balance that out with a +3. And since there's only 1 iron, there's just a 1, then that means that iron is indeed a +3. So over here we got +3 to go with the -1 chlorine. So ionic compound, swap and drop. We get 1 iron, we get 3 chlorines. Right? Boom. Done. Excellent. So next problem. Try to make this video quick. I'm going fast. You can stop. and you know, replay each individual one of these as many times as you want to, and all that good stuff. Even you could pause the video, try to work them ahead of me, and go back and do them and see if you got it right. So this guy, I have an element by itself, and then I have a compound. So that's the setup of a single replacement reaction, right? So we go on to our single replacement reaction stuff here. It's the setup of a single replacement reaction. And if I look, this is a metal. So metals replace metals. So I'm looking to see if this metal will actually replace this metal, right? So what I do there, all I have to do is check the activity series. I understand metals replace metals, non-metals replace non-metal. So since this is the metal, I'm looking to see if it replaces the nickel. Does zinc replace nickel? So the only question is zinc more active than nickel? If it is, then it replaces. If it doesn't, then there's no reaction, right? So we look on our activity series, and I know that it's hard for you to see this according to how big your screen is. But if I look, I can find zinc right here, okay? And then nickel is right down here. So we have zinc, and then we have nickel. So zinc is higher than the nickel. So since the one by itself is higher, the replacement actually happens. So, So the zinc bonds with the oxygen, and then the nickel winds up by itself. Now, metals aren't diatomics, right? So it's just nickel right by itself. This guy, just have to make sure I write its formula right. Zinc's always a +2. Oxygen the -2. So you swap and drop, you get 2 and 2, simplifies down to 1 and 1. Their charges are already neutralized. If we add them, they already add to 0, so we're good. We just need one of each, right? Once again, we don't have to leave that stuff or any of this stuff here for that matter, right? Okay, so single replacements are really easy to write. It's just, does the reaction happen? If the one by itself is higher, then the reaction happens. Now, if the one by itself was a non-metal, was a halogen, then we would be comparing it to the other halogens on this list, right? So the last one we're going to do is here. So this is obviously a compound. And then this is obviously a compound. So if I have two compounds, I immediately think, okay, it's going to be a double replacement. We talked about the exceptions up here where it actually ends up being a synthesis, where I end up with the same thing in the back in both cases, and those aren't synthesis or, yeah, that's good. So this is definitely two compounds that are two completely, four completely different things: hydrogen, sulfate, potassium, and chlorine. Four completely different things. So yeah, we could definitely do a double replacement here. So writing the double replacements, remember we said was really easy. You just switch the partners. It's does it actually happen? So here was I give you all these things, but we said, okay, this is really where it boils down to rule 7 and 8. Both reactants have to be aqueous in order for the reaction to take place. And then both the products can't be aqueous. So we need one of the products to be aqueous and then one of them to be something else, a solid, liquid, or a gas. Okay? If it meets that criteria, then great, the reaction happens. If not, then we just say no reaction. Okay? So to determine if they are aqueous, we have our solubility rules here, right? That tells us, I'm not going to go through all of these, but like for example, number 1 says alkali metal compound. So that's alkali metals are group 1. Any compound that has a group 1 metal in it is going to be soluble, which soluble means aqueous, soluble aqueous, right? Any compound that has acetate, any compound that has nitrates, any compound that has ammonia, any compound that has ammonia, all of those are automatically going to be aqueous if they have that. It doesn't matter what they're bonded to. If those things are in there, then they're going to be aqueous. And we added to that chlorates as well. Okay, so all chlorates are soluble as well. And then these others goes down and say, hey, these ones are soluble, these ones are not. Once again, soluble means aqueous, insoluble means it's not. Okay, aqueous, it forms a solution. Okay, so you put that stuff in water, it'll dissolve, form a solution. Okay, so we need both of these to be aqueous, and then we need one of these on the other side to be aqueous and one of them not. So what we do is we look at this, or we can look at the chart, which is a shortcut of those rules, but the chart isn't complete. Everything's not on there, right? So For example, this HSO4, you don't find hydrogen here on the list. Now you will find the SO4, sulfate, but you don't find hydrogen, so you can't use the chart for that. So you got to come back here and say, okay, which one of these rules applies to H2SO4, right? And of course, H2SO4 is an acid, right? So all acids are aqueous. So we come here and we say, okay, this guy is aqueous. It forms a solution. We're good. And then we got KCl, which K is potassium. Potassium is group 1. So automatically I know that it's soluble because it's a group 1 metal. So since both of those are aqueous, right, we can write the reaction. If one of these wasn't, then we would just go ahead and say no reaction. Boom, we're done. We don't have to do the problem. Okay? But they both were, so then we'll swap it up. And we just have this guy bond with this guy, and then we put these two on the inside bonding together. Okay? So I've got hydrogen bonded with chlorine, and then I've got potassium bonding with sulfate. Okay? So hydrogen +1, chlorine -1, we just need one of each of those, right? So +1, -1, so boom, that's it. I'm done with that one. There's nothing to write there. And then potassium, once again, is a group 1. Sulfate, we should know from our polyatomics, is a -2. So when I swap and drop there, I get K2SO4. Once again, I'm not trying to take numbers from this side over to this side. We're not balancing the equation here. We're writing each formula correctly for that. You know, potassium sulfate. What's the formula for potassium sulfate? It's K2SO4. Okay? So we're not done because, like I said, we need both of these to be aqueous, but then we need one of these to be aqueous and one of them not to be. All right? So HCl is hydrochloric acid. So acids are, once again, rule 6 over here, are always soluble. So this guy is aqueous. And then potassium sulfate, once again, potassium sulfate is potassium's a group 1. All group 1s are soluble. So this guy is also soluble. So I ended up with 2 AQs. Well, that's a problem, right? Because what I need is AQ here, AQ here, and then I need one of these to be AQ, and then one of these to be a solid, a liquid, or a gas. I need it to be something else. That's not what I got, right? So this reaction would not take place. I don't have to erase it. I just mark through it, and then come here below it, above it, out to the side, and say this guy is a no reaction. That reaction wouldn't actually take place. If we put those two solutions together in a beaker, nothing would happen. Okay? So I know that's not a bunch of examples, but that's at least one example of each of the 4 types to maybe review, get your feet wet, remind you what's going on there. If you have any questions about any of these, ask me. Okay? Y'all have a good one.